Okay, anyway, I will check later. I have to start talking before showing pictures, and therefore I have some time. I want to continue the discussion of climate change. Today we are finishing the lectures. One thing before we move forward, I'd like to tell you, for those of you who are interested in taking the exam on Monday, May 4th, I need to make the exam in the early morning. And so far it's fine because I have room for 4 people, and so far it's fine because I didn't get many subscriptions. And as I told you, on the 4th I can just make the exam to about 4 or 5 at most. So early morning means 8:30 sharp, okay, for those of you who subscribe, and also I will send an email to those of you who subscribe. Okay, so the discussion about climate change. I briefly mentioned to you the reasons why I want to close this subject, this course on hydrology and water resources management, by talking about climate change. The reason is that climate change always comes into play when you discuss with stakeholders about water resources planning, water resources management planning. The reason is that, of course, as I told you, there is a lot of information coming in about climate change and a lot of concern. And of course, when you make plans for the future, climate change raises concerns because it's supposed to affect water resources availability, and indeed it does. And I mentioned to you in the last lecture that climate change indeed is occurring. It has always been occurring because climate is changing. And we know that we had glaciations, we had warm periods. It was proved that about 6 million years ago, the Earth was much more warmer, much warmer than now. And consequently, the concentration of CO2 at that time was much higher. And this is the result of natural fluctuations of the climate, which, as I said, are known to occur. And they are so far poorly explained because there are hypotheses on the causes that may have triggered glaciations and raise of the temperature, but these are just hypotheses. For instance, glaciations may have been caused by volcanic eruptions, which may have increased the concentration of particles in the atmosphere, and therefore triggering a kind of screen to the solar radiations, and this may have caused a decrease in the temperature. Keep in mind that, it suffices a change of a few degrees centigrade in the global temperature to trigger a glaciation. So we don't need a change of 20 degrees to trigger a glaciation, but a few degrees are enough to revert the current retreat of the glacier and to trigger an advance of them. And basically, so one hypothesis is the possible activity of volcanic eruptions. Other hypotheses are related to a supposed change of inclination of the terrestrial axis, or other hypotheses are related to changes in the solar activity. So there are many hypotheses on the table, and it's not possible at the present state of knowledge to understand the complexity of the phenomena that are leading the climate. And also keep into account that we know that small short-range fluctuations are superimposed over long-term fluctuations. So we know about the glaciation, and we know about warm periods that occurred in the past, but we also know that there were short-term fluctuations in the recent past at different time scales. So for instance, you can find on the Wikipedia a lot of information on the medieval warm period. If you Google it, medieval warm period, basically you find a long discussion on a warm period that occurred at least in Europe around 1500. And at least in Europe, because in the Western world, we didn't have at that time measurements, of course, because America was still to be discovered or was discovered in that period. But for Europe, where we have a lot of witnesses, we don't have measurements even on Europe of temperature, but we have witnesses that, were along the generation, were passed along the generation, and these witnesses prove that in around 1500, as I said, there was a warmer period. And we know from witnesses, for instance, that people could cross from Italy to Switzerland across the Teodolo Pass. The Teodolo Pass is close to Sardinia, without touching any snow. And now there is a glacier there, even in this warm period. And also, we know that, for instance, the name of the matter or Mount Cervino in Italian comes from the Romans who named it at the beginning Mount Silvanus, which means wooden mountain. And therefore, and also we know that in the Dolomites, the trees were extended at a higher altitude, around 1500, than now. So basically, we know that there was a warmer period whose explanation is not known, so we don't know what was the cause of this warm period. And then we experienced a decrease in the temperature in Europe, and the minimum was reached around 1750, when in the Apennines there were permanent glaciers, and these were observed. There was a scientist named Lazzaro Spallanzani who made observation on the Apennines. He reported a long set of observations, not measurement, observations of the landscape and the environment, and he reported back that during summer in the Apennines he saw a lot of places where the snow was perennial. And after that time, temperature started to increase. And so it seems that the glaciers in the Apennines disappeared around 1800, and then the temperature started to increase, and it's still increasing. I will show you some graphics of the historical measurement of temperature. They start around 1850. And it's clear that now we are in an increasing phase. Still, from 2004, it seems that the temperature reached a plateau. So basically, there are these small-term, short-term fluctuations, which again are not explained, and therefore the whole process becomes very complex to predict. But still, it's a bit concerning because, of course, these changes in the climate, and in particular in the temperature. The temperature is more evident, the change in the temperature, because temperature is easy to measure, and also temperature is less spatially varying with respect to other meteorological variables. So it's clear what are the tendencies. But of course, these tendencies in the temperature trigger concerns related to possible tendencies also in rainfall and therefore water resources availability. So this discussion often comes into play, and when you discuss with stakeholders, this problem is frequently raised, and it's difficult to address because at present our information is still very reduced. Unfortunately, we don't have a climatic measurement that extend to the far past. This would be extremely useful if we had measurement of temperature starting from the Roman times. The discussion on climate change would be completely different because we could know a lot more about climatic fluctuations. Unfortunately, I mentioned to you that we started observing rainfall around 1700 and the temperature around 1800. So basically, the limited knowledge that we have make our information extremely limited. And this is the first thing that you have to get clear. Climate models, our capability to make models for reproducing climate processes, it's affected, climate models are affected by a relevant uncertainty. It is, predictions are highly uncertain. And this is one thing that you have to keep in mind, because This is not known to people. Basically, the man on the street, it's reported back by the newspapers that climate prediction depict a certain picture. And this is not true. I'm sorry to be very, very crude. And basically, our prediction of the climatic processes, I state it again, are affected by relevant uncertainty. And therefore, you know, it's not easy to reply to these claims that we need to account for climate change. Because basically, if we had a clear means to take it into account, of course it would be straightforward and advisable to take it into account. But if we don't have sufficiently reliable prediction, you understand that taking this unreliable prediction into account means using something that is in the best solution, it's uncertain and might be wrong. So from an engineer point of view, what is, this is a good topic for discussion, what is the best approach to take when your future is uncertain, when there is a situation that you cannot reliably predict? So one possibility is to use models which would deliver an uncertain output. This is one possibility. The other possibility is to assume that the situation in statistical terms will not change in the future. Because, you know, I mentioned to you that when you don't have any information, what is the best way of making a prediction? The best way is computing the average and of the observation that you may have. The best way is to collect information of the current status of the process. Let's say the easiest way is to collect information about the current status of the process and assume that it will not change into the future. This is a possibility. So basically, in terms of water resources availability, we have studied methods that allows us to estimate water resources availability. All these methods use information, they use data. Some of them require fewer data, but all of them, if you make a summary of what I explained to you, all of them need data. The data can be also your observation, but your observation is done at the present time. So reflect the current status of the system and the process. So all of these methods need data. And basically, when you make predictions, you assume that your current status of the knowledge, according to all these methods, will persist into the future. So this is what we do. And this is the second alternative, which I mentioned to you. Classical engineering studies, basically they take data, analyze the data, and assume that the future will be like the present and the past. This is our classical engineering approach. Now, in the face of climate change, people basically suggest that it would be better to use the first approach that I mentioned to you, to use climate models to gain a prediction of the future. And this is uncertain. So what is the best way forward? This is a strong discussion. So some people say you should rely on climate models and refer to future scenarios given by climate models. Other people say you should use the data and make reference to the current situation. Now, what should we do? First of all, let's try to be objective and to be engineers. According to climate predictions, basically the future scenarios depict a situation that is worse than the present one. In terms of everything. In terms of extreme rainfall, it's predicted to increase. In terms of water resources availability during dry periods, it's expected to decrease. In terms of average rainfall, it's expected to decrease. In terms of water resources availability, it's expected to decrease. So all of these predictions predict worst scenarios for the future. This is something that I never understood, why climate scientists don't highlight the positive outcomes from climate change. There are positive outcomes. Just to be very funny, I may mention to you one outcome, the increase of temperature, one positive outcome. The increase of temperature has raised dramatically the quality of the French wine. And it's really increased the quality of the French wine because they have warmer temperature, and then, the vineyards produce more wine, more grapes, and also the quality of the wine is better. So this is a positive outcome, but this is just to make fun. But there are positive outcomes. I will show you some pictures that show that the frequency of droughts in some countries of the United States is decreased. It means that water resources availability is increased. These positive outcomes, when they turn into prediction, disappear. We have only negative outcomes. So basically, from the point of view of the engineer, from the engineering perspective, what does this mean? When you design infrastructures, you need infrastructures that are heavier and are more expensive with respect to using the current situation as a reference. Because of course these infrastructures should ensure water resources availability in worse conditions. And therefore, if you build a reservoir and you estimate the size required, the reservoir will result bigger if you use climate predictions. What does this mean? It means that, as I said, infrastructures are more expensive and they often turn out not to be doable. So local administration, when you present these results, often they don't do anything because they don't have money for building such infrastructures that are built by referring to climate predictions. And this is something that I learned from practitioners, from local managers, from managers of public institutions. They say, look, I can't do anything because it seems that the situation is getting so bad that we require a lot of money to get adapted to this future situation. And this is something that we really have to avoid. One of the reasons why in Italy people, the newspapers say, we don't do anything, so floods occur, and we don't do anything, and they continue to occur. Okay, there is corruption, but another problem is that, when you discuss what to do, then there is this problem of climate change that comes into play, and basically the solutions that we propose are not doable, are not practical. And this is a big problem. It's a big problem which, it's related to climate change. So this is one first consideration that I would like to make in order to, from the engineering perspective, in order to highlight that, our first job should be to resolve the problems. And if referring to the future brings us to not to find solutions, then I would say that it's much better to refer to the current situation and resolve the current problems because they are there. So this is our first job. When we are called into play and our advice is needed, our task is to find a solution, not to be catastrophic and therefore if a solution is not doable, by referring to a hypothetical future condition, let's find a solution by referring to the current state of the situation, and then, at least we solve the local problems and the current problems. This is the first engineering conclusion that I would like to make about this. Second conclusion is related to the fact that, again, from a very practical perspective, anytime that you design something, you experience uncertainty. Of course, and particularly in hydrology and water resources management, because there is a lot of uncertainty. So basically, when you make a design, you have to be very careful, because the uncertainty could, punish your effort, could imply dramatic outcomes, and therefore it's to be reduced at most, as much as we can. Now, it can be proved, and there are studies that prove that, and, but it's also a conclusion that we can reach by intuition, that if you use uncertain prediction, your uncertainty increases with respect to referring to the current situation, which can be, you know, can be known, information can be got with much more limited uncertainty. And therefore you have some uncertainty because you don't know what the future will be. But it's much better to make the prediction by referring to the current condition instead of relying on predictions that are affected by an uncertainty that we don't know. This can be theoretically proved. Basically, you need to make a prediction of future tendencies, and therefore you have to introduce an additional model, uncertainty dramatically increases. So it can be proved that from the perspective of the engineer, if you have a prediction model and the prediction model is reliable, you should trust it. If the model is not reliable and you cannot quantify uncertainty, then it's very dangerous to trust on this model. So basically, this is to let you know that you have arguments to reply to people who may tell you that you are not considering climate change. And the reply is, look, first, I need to find a solution to the problems that you are raising, and the solution needs a practical approach. Second, practical means that if I propose a solution that is too expensive and you cannot do it, this is not practical. Second, and more important, the uncertainty in climate prediction is so relevant that from the point of view of the risk of failure, it's much better to just assume that the climate will continue in the present state. And the third thing that you could say is, what is the expected lifetime of what I am designing? Is 100 years? Okay, in 100 years, climate is not expected to change at a dramatic rate. If I had to build something that is supposed to live 1,000 years, it's another story. But in 100 years, we are not supposed to undergo changes that are so dramatical. But still, you know, it's not easy, because if you look on Google about climate change, climate scientists say that climate change will occur very rapidly. So now you may wonder, what is the reason of that? So what is the reason of being so controversial? Because if my conclusion is so clear, what's the reason why scientists continue to discuss? The problem is that climate change is a political issue. It's not just a scientific issue. And it's very political, and there is a political agenda behind it, and therefore it's, you know, it's a topic that is extremely contentious. It's extremely debated with a lot of, you know, problems when it comes into play. And you may remember that there was, I think it was the president that came before Obama, that was Bush. He competed at the election with Al Gore. And Al Gore basically based its electoral campaign on climate change, and is still continuing. And therefore, you know, the election of the president in the United States depends on climate change. And also some wars were triggered by concerns related to climate change. So it's very political. Okay, now let me show you some evidences and something that you can find on the web. And let me anticipate that, you know, again, if you look on the web, it's extremely difficult to get information on climate change because you get millions of entries, and there is it's not easy to select the information to get an objective view. And I try to show you some sites. And first of all, let me go, if still the connection, let me go to the NASA website, NASA. So basically, you jump here, climate change and global warming. This website is extremely skeptical. So basically, I may show you some. Let me see if it's enough. Just 1 second, let me see NASA global temperature. Because in this way I directly jump on this page, which is No, this is the previous one. Sorry. Okay. This is the website where I wanted to go. If it doesn't, okay. This is basically, this is a graph of the global temperature from 1880 to 2014. First of all, let's assume that this is reliable, because if we enter into the discussion of how global temperature is measured, we get lost. So let's assume that this is reliable. And there is a lot of scientific discussion on the reliability of these observations, because of course now we have many more temperature gauges around the world than in the past. So basically these data were computed by considering only a limited portion of the temperature stations that we are using now. And there are some concerns because of two reasons. First, the increased density is not really representative of the global distribution, because over the oceans we don't have any measurement station. And the oceans, you know, they are the bigger part of the Earth, so basically they cover the majority of the Earth's surface, and therefore the fact that the density increased only over the length, you know, it brings some uncertainty into play. And also there are some stations that are located now into the cities, and there is the heat island effect that is causing noise. And in particular, in this region we have some temperature stations that are located, for instance, one in Modena, and they detected a much higher climate temperature change during the history. They work from 1880, and the temperature increase is much higher. And I raised the problem of the heat island effect, and they said it doesn't exist, which is not true, because it's clear that the expansion of the urban area is caused with respect to, you know, to 1900. The size of the city is dramatically increased, so it's not true that the effect doesn't exist. The problem is that we cannot quantify it, so it's easier to say it doesn't exist. But so even in this case, many of the stations are located into the cities, and therefore it's not clear. But let's assume that it's reliable, because otherwise, you know, this is a problem. First of all, what you can see is some fluctuations, long-term ones, because you see 1900, 1910, 10 years of decreasing temperature. And then there was an increase up to 1940, and then stable condition up to 1980. And you see that around the 70 there was a minimum, a local minimum. Around that time, basically people were much concerned by the global cooling. So if you Google global cooling and you go back to this period on websites describing what happened here. And basically, there were much concerns because people were concerned by an incoming small glaciation. And then temperature started to increase again, and therefore these concerns disappeared. And it started to increase about around 1980. And what you see, first of all, this graph is centered around the long-term average. So 0 is the long-term average in this period. So basically, as you see, in 1970, there was this cold period, and then temperature started to increase. Indeed, the increase from 1980 to 2000 is quite significant. And this brought scientists to say that this sharp increase was never experienced before, ever, but by the Earth. This is a conclusion that is, of course, not supported. We can't know that. But indeed, the increase is quite sharp. And the slope is higher than the slope of the increase between 1910 and 1940. But you see that from 2004 there is the plateau. And this red spot here is 2014, because NASA claims that 2014 was the warmest year ever. Then they corrected the warmest year on record, which is true. I mean, if you look at 2014, it's the warmest according to this record. But there is to say that the difference between 2014 and 2007 is limited, and 2013 was, and also 2012, they were colder. So basically the result is that there is a plateau here, and there are models predicting now a decrease of the global temperature up to 2030. We will see. Okay? And an important thing to say, this plateau was not predicted by models in 2004. So up to 2004, scientists were predicting a sharp increase, a continuation of this increase with increase and slow. Unfortunately, this did not occur. And there is, I have a picture. I have to find it, just 1 second. Okay, it's this one. These are, the black line is the observations. And you can see, and these are predictions that were issued a long time, starting from 1980, and many of them were raised around the 2000, the year 2000. And you see that the predicted temperature, the average prediction was, at that time, for a situation which, where the temperature was supposed to be about 0.5 degrees higher than now, which means that a situation that would be really warmer. And this didn't happen. And this is the current situation, and of course, let's see what happens in the future. Basically, you find some websites where scientists admit, and also the International Panel on Climate Change admitted in some circumstances that their prediction turned out to be wrong. First of all, look at the variability. I mean, if you ask them, they say yes, but I'm still into the range. But the range is very wide, so it would be impossible to go outside the range, I think, in 10 years. Maybe that in the next 10 years, we get outside from this range. But the fact that we got close to the minimum, it means that, you know, all of these predictions were dramatically wrong. If you look at the upper ones, they are plain wrong. And also there was an interesting graph. Let me see if I can find it. There is the hockey stick controversy. There was a prediction that was raised around 2000, which that was obtained, developed around 2000, which triggered a lot of discussion. Basically, this is the hockey stick controversy, the picture of the hockey stick. So basically, you see that observations were available up to 2000, and these are centigrade degrees. You see that what was the prediction? Sharp increase, which didn't happen. Anyway. So this is just to show you what is now the situation for temperature. Now let's look at rainfall. And I have some pictures. First of all, look at this graph. This graph is taken by the website of the Environmental Protection Agency of the US. Look at the outcomes from climate change. None of them is positive. So basically, the dominant word is increase. And when there is a decrease predicted, is in any case for the worse. So basically, increased water used by plants, increased evaporation, increase in sediment and runoff, increase in water temperature over time, decrease in late summer water flow with increased water temperature. Keep in mind that increased water temperature means decreased water quality. They are strictly related. More severe drought, decrease in lake highs, increase the potential of transpiration, increase in rainfall from heavy precipitation event, just heavy precipitation because it's not useful. If it was an increase in rainfall, average rainfall, it's very useful because it's water resources. Heavy rainfall is not useful. So basically they predict that heavy rainfall will increase, but average rainfall will decrease. And then decrease the snowpack. Decrease in light rains, so increase in extreme rains, decrease in light rains. Reduction in runoff. Earlier peak stream flow. Increased water usage because of warmer temperature. So this is what will happen. according to this graph. Now let's look at precipitation from the same website of the first. This is a website of the Environmental Protection Agency again. This is rate change of precipitation, and it's percentage per century. So basically, this is the change that is expected to occur in 100 years. And the gray interval is basically no change. -2 plus 2% in 100 years is nothing. So the gray region, they are not expected to change. And the light green, we expect a change that is below 10%. And basically, where you see brown, it means decreased precipitation. When you see green, it's an increased precipitation. And this is average precipitation. So basically, the situation is not so bad. I mean, there is an increased precipitation over the United States, which means that drought, the frequency of drought, is expected to decrease. This is also reported. I think I have here the graph of the drought. Let me see. I have to check where. No, sorry. This is nothing. And this is another record of global temperature, because there are many agencies computing the global temperature, but you see basically more or less it's the same thing. You see the plateau here from 2004. This is precipitation worldwide. So look at this graph. Basically, this is again from the NASA website. They say that this is a clear indicator of climate change. And really, I don't see any climate change here. I mean, while with temperature you see a clear tendency, with rainfall, below average, for a period, a certain period above average, and then above average, again below average, and now above average. But if I look at the shape of this graph now, and 50, 60 years ago, I mean, this is global temperature, global solid rainfall. And now if we look at the United States, and this is another